Yes. So first of all, what is data parallelism and what is task parallelism? So first, data parallelism means that we in parallel execute the same value or same operation on different values, and this is also known as loop parallelism, where we execute the same operation on different iterations of a loop. And the other form of parallelism is task parallelism, where we in parallel execute possibly different operations. And you may also know this as control or functional parallelism. If you then look at array languages, then you could view data parallelism as the parallelism within array operation and task parallelism as the parallelism between different array operations. And the parallelism within an array operation is usually quite large, because we perform array operations on large arrays, and that gives huge potential for parallelism, whereas the parallelism between array operations is usually little, but that of course depends on the exact program that you're executing. Then, if you're implementing an array language, and quite a few of us are doing that, then you can make the choice whether you want to exploit only the data parallelism or want to exploit both data and task parallelism. So first option would be to only exploit data parallelism, and the advantage of that is that you can then use a scheduler that is made specific for data parallelism. The other option would be to exploit both data and task parallelism, and what people typically do is that they implement data parallelism via task parallelism. So in this example, I have some data parallel operation B, and I can split that operation B into multiple tasks. And there are various ways to split such data parallel operation into tasks. I won't talk about that, but yeah, the downside of this is that we're now using a task parallel scheduler to schedule this data parallel workload. And I think, yeah, all the languages that are present here fall in one of those two categories. So I think SEC falls on the left side, where they only have a data parallel scheduler. Futark is, I think, on the right, where they use task parallel scheduler. Is that right? It's more complicated than that. Okay, and an APL, for instance? Okay, that's also complicated. Anyway, so there's kind of a gap that we have, and work assisting tries to fill that gap, because in work assisting we have task parallel scheduler for the task parallelism within a program, and then we have a data parallel scheduler for any data parallel operations within a program. And then we can exploit both forms of parallelism while still having a data parallel scheduler. So our work assisting scheduler is the link between a task parallel scheduler and a data parallel scheduler. And primarily we use the task parallel scheduler to distribute work. So whenever a thread needs new work to work on, it will use the task parallel scheduler, and it will try to claim a new task. If there are no such tasks available, then a thread will attempt to assist with the data parallel operation of another thread. And to do that, threads share their current data parallel computation, so that other threads can find this computation. Then the workload in such a data parallel operation is scheduled using a data parallel scheduler. Our scheduler is a dynamic scheduler, similar to work stealing and self-scheduling, which means that it schedules the workload during the execution. And this way it can properly balance the workload over the available threads. Specifically, this means that when we're executing a data parallel workload, more threads can assist in that data parallel workload. And this allows it to properly balance the work, and it basically provides the same flexibility as work stealing does, if you compare this to a system where data parallelism is implemented via task parallelism. And this is in contrast with existing schedulers for mixed data and task parallelism, because those typically fix the number of threads at the start of a data parallel workload, whereas we allow more threads to join a computation whenever they become available. This setup provides two main advantages. First is that data parallel workloads are scheduled with a data parallel scheduler, which is required by certain data parallel algorithms. And data parallelism is only exploited if task parallelism is not sufficient. As an example of that are zero overhead parallel scans, which I will in fact present directly after this talk, benefit from both those advantages because they require a specific order in which work is claimed in that data parallel workload. So they really require a data parallel scheduler because task parallel schedulers typically cannot guarantee that. And they have a fast single-threaded mode, which is faster than the parallel mode, and they operate in that mode as long as only one thread works on the scan. So hence it's beneficial to first exploit task parallelism and only exploit data parallelism if that's needed to saturate the processor. So that's a bit of the context that we're in. Let's now look at how we implement that. First, let's look how we model a data parallel workload. So we call a task with a data parallel workload a data parallel task. And in this example, we have several tasks, but task B is a data parallel task. And it consists of two phases. First, it has a parallel phase where we do the actual parallel work. And then we have a finish phase, which is executed when all the parallel work is finished. And the finish phase is executed by one thread. Example lifetime of a task can look like this. Thread 0 starts some work on a data parallel task, and it first shares that task so other threads can observe this task. Then it starts working on that parallel phase. Then after it has done some work, thread 1 finds this task because it was looking for something to work on, and it will assist in this task, and it will also help in the work phase, and thread 2 will then also do that. And at some point, all the work is being claimed, and a bit later all the work is finished, and then those threads will exit from the work phase. And thread 1 is the last thread to exit from the work phase, and that thread will execute the finish phase. Typically the finish phase will start other possibly data parallel tasks to continue the computation. So let's first look at this parallel work phase. I should say this is the only slide that contains some actual code, so I hope you can deal with that. So for the work phase or the parallel phase, we need to define a work function which describes what should happen there. And this function is called by the thread that starts this data parallel operation and by any threads that assist. It gets several arguments. First is a pointer to some data, and that's whatever data you need for this task, similar to the context of a lambda function. And this function will then, in a loop, do some work for block I, and that variable I is first assigned the value of first index, and first index is the index of the block that was claimed by the caller of this function. So the scheduler first claims one block, and then this thread will work on block first index. And when it's done with that, then it will, via an atomic increment, claim the next block. And this is basic self-scheduling that you may have seen before, dynamic self-scheduling. And you can also have other data parallel scheduling algorithms, but this is just a simple example for that. Then at some point all work has been claimed, because we're now with this atomic fetch and add constantly claiming more work, and at some point all work has been claimed, and then we should inform the work assisting scheduler that all work has been claimed. And we do that by calling this function signal task empty, which essentially tells the work assisting scheduler that it should not tell other threads that they can assist on this task. So it will stop sharing this task to other threads. Then, where the comment is, we do the work for block I, and that should be sufficiently large amount of work to not have problems with scheduling overhead. So we typically implement some kind of tiling or some blocking. And then do work for all the elements. And to make it concrete, I can, because this is the basic boilerplate that you would need for any work function. To make it concrete, I can now convert this into a work function for a parallel reduction or a fold. To implement that, I would need to add some values to data, because I need to have an input array and I need to have a place to store the output. Then I want to store the sum for all the work of one thread in a local variable. So that's what I do in that variable local sum. Then at the place where I would need to do work for element k, I read that value from the array and add it to the local sum. And at the end, I add the local sum to the global output. And then when all the threads have finished the work function, we know the total reduced value of this array. So that's the work phase of a data parallel task. When all the work is finished, we call the finished function, and the finished function is executed by one of the threads that was working on this task in the parallel work phase. And in this finished phase, we typically spawn new tasks, which could be data parallel tasks. And that, of course, depends on the program. So those are the work and the finish phase. And in the beginning, we need to share this data parallel task, such that all the threads can observe this task. And we do this by maintaining a global array containing the activities of all the threads. And this array is also called activities. And when a thread is working on some data parallel computation, it will announce that in this array. So it could, for instance, be in this example that thread 2 announces that it's working on a parallel reduction. And then any other threads that have no work for their own to do can assist in this parallel reduction. Well, we need to make this a bit more concrete, so let's see what we need to store in such a task object. Well, first we need to store the function that any assisting thread would need to call. That's the work function. We store a pointer to that function in the task together with the data or context for that function. Then we need to be able to communicate how much work has already been claimed, and for that we store a work index in the task together with the total size, so the number of blocks for this data parallel computation. Then we also need to know when all the work has been finished, because now we can see when all work has been claimed, but we also need to know when all work has been finished. And for that we keep track of the number of threads working on this task currently, which is kind of the reference count of this task. And we store that in the field active threads and in activities. So we split the reference count essentially over two places for a reason that I'll explain later on. But if you've ever done something with concurrent reference counting, then you may have seen this before. Then finally we store a pointer to the finish function, which is called in the end. So now we can do a small simulation of how the work assisting scheduler could execute this task. So this task is now shared in activities, so any other thread can find this task. And when it finds this task and wants to work on it, then it will increment the number in activity. So that's currently a 0, but when another thread finds it, it will increment it to 1, and perhaps another thread joins, and then it becomes 2. These threads will gradually work their way through all the work for this task, and they do that by incrementing work index. So that's currently 1, and that will increment to 7, and so on. Oh, 15. And at some point, there may also be another task that becomes available, and another thread is working on that, and that will also increment the work index of that task, which will eventually finish. And then perhaps that thread that just finished that task will also start assisting on this data parallel task. So now there are 3 assisting threads, so 4 threads in total working on this task, and they will eventually increment work index to the last block. And at this point, this task doesn't have to be in activities any longer because all work has been claimed, so no other thread can help. And we then remove this thread from activities and move the reference count to the task object. So now we'll store 4 inactive threads, and then whenever a thread is done with this task, it will lower active threads, and eventually that becomes 0. Then the finish function is called, and then the task is deallocated. So you saw that I did some weird things with that reference count because it's placed in 2 locations, and that's because we're now dealing with concurrent reference counting. And in concurrent reference counting, you can have annoying race conditions, and we can prevent them if you can assure that incrementing the reference count and acquiring the pointer happens atomically. And we can do that by storing them both in the same word. What we concretely do is that whenever we increment the reference count, that happens in activities, in the count in activities. When we decrement it, we do that on the active threads in the task object, and this function signal tasks empty, which is called when all the work is claimed. That moves the reference count from activities to active threads. This is essentially a simplified version of the split reference count technique. If you want to know more about that, then here is some suggested reading. Then we did some benchmarks. First benchmark was lower-upper decomposition of matrices. We did this of multiple matrices at the same time, where the outer level of outer parallelism is that we're doing this on multiple matrices at the same time. And the inner level is the parallelism within one matrix. And the outer parallelism is implemented as task parallelism, and the inner as data parallelism. And here are some results for that. So we did this both on an AMD processor and an Intel processor, because scheduling may differ per machine. And on the left we have 1 matrix, and on the right we did this for 8 matrices. And as you can see on the left, it's difficult to execute that in parallel because there's just not enough parallelism. Whereas if you have 8 matrices, then it's a lot easier to exploit the parallelism. So the red one is our implementation, and then the purple open circles is an implementation with work stealing, and then the others are OpenMP, using the Clang implementation. And we're competitive with, are better than the alternatives. Especially on the right, it's interesting that we have 8 matrices, but this also scales to more than 8 threads, so then we really need to use both levels of parallelism. Then we also did a compaction benchmark. I'll quickly go through this. Compaction was one of the algorithms that had a special single-threaded mode. But more on that in the next talk or in the paper. Because I'm also running a bit short on time. Then finally, Quicksort. Quicksort is a divide and conquer algorithm, and we implemented partitioning as a data parallel operation and the recursive calls as a task parallel operation. And the contribution of data and task parallelism varies throughout the execution of the program, because in the beginning there is one large data parallel operation, and at the end there are many small tasks. And the scheduling algorithm should work well both in the beginning and in the end, of course. So here are the results. Again, the red line is our implementation, and we compare that with work stealing, which are the open circles, and OpenMP implementations. And the green line is one where we do partitioning sequential. And you can see, first of all, that scales poorly, and that we are competitive with work stealing implementation and one of the OpenMP implementations. and those are the results on an Intel processor. I think the OpenMP implementation also had some higher single-threaded performance, which made the comparison a bit harder here. But yeah, to conclude, work assisting provides the link between the task parallel scheduler and the data parallel scheduler, such that you can use both in the same program. It first only exploits task parallelism, and when needed, it exploits data parallelism. And yeah, work assisting is competitive with or faster than implementations that handle data parallelism via task parallelism and use work stealing. Thank you very much.
Questions? Thank you for the nice talk, Ivo. My question is, what do you do if you have multiple tasks that do data parallel operations? How do you split the machine?
Okay. So if you have multiple data parallel tasks, then there will be multiple entries in activities. So then you'll be in a situation like this one. And if a thread now is searching for a data parallel task, then it will traverse activities in some order. And the order in which it traverses that will denote whether it finds the left task or the right task first. Which is somewhat similar to work stealing. If you are in work stealing and you need to claim a task from another thread, then you'll traverse a list in some specific order, perhaps randomized order, in a specific direction. And you can tune that perhaps also with a NUMA architecture to make sure that you choose the right one. But in the end, we just choose the first task that you'll find. But yeah, you could do more sophisticated things, perhaps. Yeah. So the implementation that we do, that we have in our benchmarks, is that you traverse the activities array starting at your own thread index and then going left or right. So half of the threads go to the left, half to the right. It's a bit of an ad hoc order, perhaps, but it worked well in our benchmarks. But we didn't do experiments to see if a different order would be better. I guess a randomized order would also be fine. There's some choices to be made there.
Right. Me next. All right. So one thing I always find challenging when writing these work stealing schedulers is figuring out the right chunk size. In your one benchmark, it seemed like it was hard-coded. Is that just what you do, or do you have something more advanced?
Yeah, that's a good question. So in work stealing, when you split tasks, you should at some point also decide how large those tasks should be. And we somewhat have a similar problem, perhaps slightly easier problem, because in the work function you also split the work into blocks, chunks, and you should tune that. In our experience, you can somewhat easily find the right size by running the program on a very large input size and starting with a large block size and just lowering the block size until you see the scheduling overhead. Because then you'll find the block size at which the scheduling overhead is just only just invisible. And then you can find a appropriate block size. There are also alternatives because this idea of self-scheduling has been around for a lot longer. There are also, I think it's called trapezoidal self-scheduling, where you in the beginning have a larger block size and the block size slowly decreases. So that at the beginning you have a large block size which gives you low overhead. And at the end you have a smaller block size which makes it easier to balance the work near the end. Because in the end it's important that work is properly balanced.
All right, thanks very much. The next talk,